Good afternoon, students. So just want to go over the final study packet today for pre-calculus honors class. So I'll just set up the basic step or the initial step for each problem, and then for the rest of this, you guys should be able to do it. Okay, so here's some of the simple questions that you're going to be dealing on the final. So the first set, it's about finding the derivative with the limit definition. Okay, so let's start it off with number 4. So since they're quite similar, so I'll just do one problem from each set. Again, it's about the setup. Okay, so let me go to Active Inspire. Okay, so copy and paste right here. So the first one is about the rational functions. So how do we find out the rate of change or the instantaneous rate of change for this functions, the derivative? So the way to do it is by using definitions. So limit h goes to 0, f of x plus h minus f of x all over h. So the setup here, it's a composite function. So started with limit h goes to 0. So f of x plus h for this rational function that would be written as negative 1 over x plus h plus 1 minus f of x, which is the original function itself, and then all over h. So this one you can simplify it. And then the next step here, you want to find the least common denominator. So the least common denominator, it would be x plus h plus 1 times the quantity x plus 1. So make sure that you know how to find a way to convert those rational expressions to the least common denominator form. Okay? So you want to find out more problem like this, so you probably want to watch the other part of the video. So the latest one that I put up there for the lecture, the derivative, which is about 2.6 for calculus. Okay, so now let's see what else that we have for the rest of this. So going back to this template. So the other one is finding the limit as x approaches infinity. Okay, so x approaches infinity. Okay, so let's do one of those. Okay, what about number 8? Okay, so for number 8. So this one basically using the properties of limit. So this one you can see that it's a quotient and then the sum. For the sum, we can always separate it out. So the negative 1, you can put it out. So e to the power of x over x to the power of 4. And then the other one is the limit as x approaches infinity of the constant function, 1. So the function for the constant, 1, x goes to infinity. So no matter how big that x is getting to, so the constant, it's always the constant. And then for the most difficult part, it's about the comparison of these two. So L'Hopital's rule, you guys haven't learned about that yet, but here's another way to analyze the infinity, e to the power of infinity, infinity to the power of 4. Negative 1, just carry that over. So back to that, the algebraic function, so exponential growth, which is going this way, and then x to the power of 4, so that means it's just like a kind of like a U shape, but the U shape's a little bit flat right here at the 0, because that has like a multiplicity with 0 for repeating solution. So, and by the time they compare that, the rate of change right here, as you can see that the tangent line, so the slope of the tangent line is getting deeper and deeper for the slope. And compared to this one, so obviously the exponential growth would be growing faster compared to that, the x to the power of 4. So that means this one, the infinity on the top, would be a whole lot bigger compared to the infinity down the bottom. So this one basically can treat it as negative infinity all over a constant plus 1. So eventually it's going to be negative infinity plus 1, which is considered negative infinity. Okay? So that's for number 8. And now let's see what else that we have for the rest of this. So it looks like yet a set of problem. We're dealing with the parametric equation. So anytime that we want to sketch the graph for the parametric equations, the first thing that you want to do, so you want to convert that back to the rectangular form. So convert it back to the rectangular form. So now let's look at that number 10. Okay, so for number 10. So first thing that you want to do, so basically you want to divide both sides by 2. Okay, so divide both sides by 2 for the x parametric equation. So divided by 2. And then for y, so that one you want to divide both sides by 3. So the purpose of that we're doing this one, because we just want to make sure that tangent and secant are being isolated. So once we've been able to isolate that tangent and secant, so we'll be able to square both sides. So square both sides. Square both sides. So it's x to the power of 2 over 4. So that equals tangent square of t over 2. And then the other one, y squared over 9. So that equals secant square of t over 2. And then from here, would you know that secant squared minus tangent squared? Then that'd be 1. Okay, so y squared over 9 minus x squared over 4. So that equals secant square of t over 2 minus tangent square of t over 2. So this one turns out to be 1. The Pythagorean identity. So it's y squared over 9 minus x squared over 4. So this one is just like going back to the hyperbola, conic sections. So any question that regarding the way I sketch the hyperbola, so make sure that you refer back to the graph. So things that I talk about in algebra 2. So type in that conic sections, hyperbola, and you'll see that the way I sketch the graph for that. And also it's a parametric equation, so make sure that you need to set up the pathway for that, the parametric equation. Also, you can refer back to pre-cal lecture 9.6, and that's the exact same content I was talking about. Okay, so now let's see what else that we have for the rest of this. And the next time, so this one is 13 to 18. It's about classifying the polar equation, writing the equation for the polar graph. Okay, excuse me for a second. Let me keep the door closed. So for this type of problem, as you can see that, you'll see the paddle, the rose curve, the limicon, and the lemniscate, and also that the other rose curve, the circle, and the cardioid. So this one can definitely refer back to one of the unit we were talking about. So back to 8.1, 8.2, 8.3, the polar equation. So if that's a circle graph, so that it's always, well, this one can be written as r equals a, so where a is a real number, and or also can be written as r equals a cosine of theta, or r equals a sine theta, so where a is the diameter of the circle. So we generate the circle either along the x-axis or the y-axis. And also can be written as r theta, so that equals a cosine theta plus b sine theta. Okay, for the circle. So if that's a line, can be written as theta equals pi over the angle, or r equals a times secant of theta, like that. And then the cardioid. So the cardioid, the relationship is always written as r equals a plus minus b sine theta, like that. Okay. And this one is showing that a equals b. Well, is that always true? Is that necessarily to be true? A equals b? Well, if you try to compare that to the limicon, which is the one with the inner loop, so it shows that a is less than b. Okay, so let's do one problem like that. And then the rose curve is just about the paddle. So a, which is the radius, so the rose has n leaves if n is odd. Okay, so n is odd number, so that has n leaves. If that 2n, okay, so if the rose has 2n leaves, so that means n is even. Okay, so got to be careful which one to apply. So it could be written as either r equals a sine of 2 theta, or it could be written as r equals a cosine of 3 theta or 4 theta. Depends on that, the number paddle that you have for the rose curve. Okay, so now let's go back to this page. Okay, so to this one right here, the final study packet. Okay, so let's check it out, that number 18. So this one is the cardioid. Okay, so let me just pull this out. Or perhaps we can just do it right here. Okay, so that's a cardioid. So according to the structure, it's either written as y equals a plus minus b sine theta, or y equals a plus minus b cosine theta. If this one is just like an up and down cardioid, facing upward, downward, so it could be either it's just a plus minus b sine theta. So if the cardioid is facing up or down. If the cardioid is facing sideways, then that'd be the cosine of theta. Okay? So this one's to the left, facing to the left, or facing to the right. Okay, so let's pick some point here. So theta, when theta equals 0, so the radius would be considered 3. Okay, so instead of using y, we're using r. It's a polar equation. So theta equals 0, so r equals 3. And then theta equals pi, and also r equals what? 3. And then theta equals pi over 2. And then radius here, then that we consider all the way through 5. So basically by using this, we can set up the equation. So 3 equals a plus minus, we don't know what that is yet. So we do know that's sine. So b sine of 0. And then the other one, so pi over 2. The radius would be 5. So a plus minus. So this one, it's b sine of pi over 2. Okay, so if you do notice that, so sine of 0 is always 0. So times b is 0. So that means what's left here? So a is 3. Another thing that you notice, so this one, if a is 3, so in order to solve for the rest of this, so we do know that this one is going to be considered sine of pi over 2, which is 1. Okay, so 1 times b, that's b. So that means 5 equals 3 plus b. And the value b, then that will be considered 2. Okay, so the cardioid. Okay, so what we got here, so this one, the radius, which is considered 3 plus 2 sine theta. Like that. Okay, so now let's see what else that we have for this. And this one, it's about the rose curve, the paddle. So as you count it, so this one has 5 paddle. 1, 2, 3, 4, 5. So according to that, the template. So if n is odd, so that means it shows the number of paddle. So n has n leaf if n is odd. So this one can be either written as r equals a cosine of 5 theta, or r equals a sine of 5 theta. But this one, according to the template, the graph, so this one, it shows the line of symmetry, the y-axis. So that shows the line of symmetry, y-axis. So most likely, this one's going to be the sine curve. Because that's sine of pi over 2, then that'd be 1. 1 times 7, then that'd be the radius. If that's a cosine curve, cosine of pi over 2, everything turns out to be 0. So this one we consider r equals 7. So sine of 5 theta. Okay, so 5 paddles. So count it. So 1, 2, 3, 4, and 5. Okay, so check that. So 5 paddle, odd number, n paddle, and then sine of pi over 2. Or sine of 5 pi over 2. So going back to this position, which is 1. 1 times 7, 7. Sine of 5 times 3 pi over 2. Then that'll be 15 pi over 2 down here. And this one shows that it's, well, nothing exists, because that is going to be considered 0 for that 15 pi over 2. Okay, so it's all about the number of paddles. Okay, so now let's see what else. And then the limicon is quite similar to that a plus minus b sine theta, or a plus minus b cosine theta structure. So this one, it's a sideways limicon, so most likely it's going to be considered cosine. So again, pick some number and then find out exactly what a and b, those numbers are. Okay, so for the next set, it's about solving trigonometric equation. So we'll do one of those. So if you look at that for number 20. Okay, so again, anytime that you want to solve for this, either we want to apply the identity. If there's no any special identity we can apply, so that means we can always rewrite the equation in terms of sine and cosine. Again, this one is all going back to chapter 7, 7.5. Okay, so let me put it out. Okay, so you may notice that negative cotangent theta, negative 3 cotangent of theta, so basically we can just group them together. So take this one all the way back to the left, so we end up with negative cotangent of theta plus 3 cotangent of theta, which is 2 cotangent of theta. So that equals root 2 cosecant of theta. And then this one can be written as 2 cosine of theta over sine theta. And then get this part right here, root 2 over sine theta. And then we try to group those rational terms together, so bring them together. Subtract root 2 over sine of theta on both sides. So 2 cosine theta over sine theta minus root 2 all over sine theta. You know, for some student might be wondering, can I cross multiply and then try to solve for one of those trig functions? Usually it's better to just put in all the rational functions together because you want to combine them. So it's 2 cosine theta minus root 2 all over sine theta. And we do know that the denominator cannot be 0. So the only thing that can be 0 here, then that would be the numerator. So 2 cosine theta minus root 2 equals 0. So 2 cosine theta equals root 2. So cosine of theta equals root 2 over 2. And don't forget about this. According to the instructions, it's showing that the restriction, it's all the way from 0 to 2 pi. And where 2 pi, it's not included. Okay, so going back to 7.5, so take the inverse of root 2 over 2 theta. So that means theta is considered 30 degree, pi over 6. And also this one is a positive ratio. So besides pi over 6, what else could that be? And also it could be 11 pi over 6. Okay, in quadrant 4. So 2 solution. Alright, and now let's see what else that we have for the rest of this. And then the other one is writing trigonometric expression as the algebraic expression. So we'll do one of those. So this one that requires the restrictions for the inverses. Okay, so we'll do 27. So we need to start it all with the restrictive range, the standard restrictive range for inverse of cosine. So let's go through that restrictive range for that inverse. Okay, for the inverse of cosine, the restrictive range is always from 0 to pi. Okay, so it's included. And then for the restrictive range of inverse of tangent, so this one is always from negative pi over 2 to pi over 2. And where negative pi over 2, pi over 2, they're not included because the vertical asymptote for the regular tangent functions. For the inverse, then that would be the horizontal asymptotes. And then, what else? Inverse of sine. Inverse of sine is quite similar to the restricted range with that inverse of tangent. So this one, negative pi over 2, all the way to pi over 2. And they're all included. So this one you can always go back to section 7.4, Pre-Cal Honors, the lecture note video, the one that I put up there. Okay, so 27, restricted range for inverse of cosine. So this one is bounded from 0 to pi. So let's make a semicircle. And we do know that the ratios for cosine is x over 1, adjacent over hypotenuse. So positive, so that means the triangle, it's in the first quadrant. So adjacent over hypotenuse. For the opposite, so that means by using the Pythagorean theorem with the ratio, so we do know that it's considered square root of 1 minus x squared. And here's where theta is. So inverse of cosine of any ratio, doesn't matter what kind of ratio that is, once you take the inverse, you always get the angle. So this one basically just showing that it's tangent of theta. With the same diagram, tangent of theta, opposite over adjacent, so square root of 1 minus x squared over x. Okay, so that's what we got for the rational expression. Okay, so now for the rest of this, inverses, this one is just like going back to algebra 2. So once everything is written in terms of x and y, so you swap the variable. So we'll do number 30. So x equals log base 3, 10 to the power of y plus 3 over 2. And we do know that's a logarithmic form. So let's convert it back to the exponential form. So this one is written as base 3 to the power of x. So that equals the results, which is 10 to the power of y plus 3 all over 2. And then the rest of that, try to isolate y by itself. So basically multiply everything by 2. So 2 times 3 to the power of x. So that equals 10 to the power of y. And then plus 3. Subtract 3 both sides. And again, this one is just that the exponential form. Convert it back to the log form. So it's log base 10 of this whole quantity. 2 times 3 to the power of x minus 3. And then equals y. And this one can be written with the inverse of f of x. Okay, so now what about solving the nonlinear inequality? So nonlinear inequality compared to the linear inequality. So that one is just consider isolating the variable. But this one, we don't just isolate the variable. We need to find out the possible zeros and the restricted value so we can perform the sign test. Okay, so let me show you one of those. Number 35. Let's see what that is. Okay, so again, I'll just show you that the structure, this setup. Okay, so negative, negative, so you probably consider doing that, divide everything by -1. We can do that, but you got to be very careful. It's inequality. So anytime that you multiply or divide it by a negative number for the inequality, we always want to switch that less than to greater than or greater than to less than. So this one started with less than, so it turns out to be greater than. And then from here, so a lot of students might be thinking about that, can we cross multiply? If that's inequality, you don't want to cross multiply. So you want to bring all those rational terms together. So it's 1 over x plus 4 minus 2 over x plus 3. Greater than 0. And now from here, convert that to the least common denominator form. X plus 4, x plus 3. Okay, x plus 4, x plus 3. And then you multiply the missing binomial, top and the bottom. So this one we need x plus 3. Over here, we need to multiply by what? X plus 4. Distribute, so we got x plus 3 minus 2 times x, and then 2 times 4 plus 8. So combine this all together. So x minus 2x, negative x. 3 minus 8, negative 5. And as you can see that we can get a 0 and also the restricted value. So we do know that x could be negative 5, then the whole thing would be considered 0. So x equals negative 5, then that means the inequality is going to be 0. And also the restricted value, so x cannot be negative 4, x cannot be negative 3. And then with all those possible 0, the restricted value of x. So we want to run through the sign test or the line test. Okay, the sign test. So the real number line here, so from negative infinity to infinity, so we put in those number from the least to the greatest. So negative 5, so that would be the 0. Negative 4, not included because that would be the restricted value. Negative 3, that's not included. So we do have 1, 2, 3, 4 different interval to verify. And for those you might be wondering, how do we verify this? And also, again, you can refer back to this one to 1.4 to 1.6 for the lecture for the sign test, inequality. And the factor we have right here, negative x minus 5, the factor, x plus 4, and the other factor, x plus 3. And then the results. So any number from negative infinity to negative 5, so negative 6. So plug in negative 6, so positive 6 minus 5, positive. Negative 6 plus 4, negative. Negative 6 plus 3, negative. And then positive times negative, it's all positive. Greater than 0, check. That's the result we want. In between negative 5 and negative 4, negative 4.5. So negative 4.5 minus 5 is still negative. Negative 4.5 plus 4 is still negative. Negative 4.5 plus 3 is still negative. So negative times negative divided by negative. Then that's going to be all negative. Obviously, that we know. And then the next one, negative 4 to negative 3, negative 3.5. So negative 3.5 minus 5 is still considered negative. Negative. Over here, well, this one would be positive. Negative 3.5 plus 3, then that would be negative. So negative, negative, positive, it's all positive. Is that the result we want? Yes. And then finally, anything that's greater than negative 3 is 0. 0 minus 5, negative. 0 plus 4, positive. 0 plus 3, positive. So negative, positive, positive, negative. Is that the result we want? We need something greater than 0? No. So the only solution we have for this one, negative infinity to negative 5. Union, what else? Negative 4 to negative 3. And make sure that negative 5, it's included, because that's a possible 0. But negative 4, negative 3, they're not included, because those are undefined situation. Okay, so now, going back. Okay, let's see what else that we have. And finding that the rest of the roots. So we actually went over that during class today. And also this one can refer back to chapter 3 for the polynomial. Finding the rational zero, the irrational zero, or the one that's given with one of the complex zero. So you want to use that the conjugate theorem to figure out the divisor and then perform the long division. So I do recommend you to refer back to section 3.4, 3.5 for the lecture video regarding this type of problem. So again, I can show you one of the setup here for the divisor. So 38. Okay, so let's see, press something wrong here. Okay, snipping. It's not working. Here we go. So anytime that one of the complex zeros is given, you can always set up that the divisor immediately. So the conjugate, it's also considered the other zeros. So the one that's given here, 2 plus 2i, it's one of the complex zero. So that means 2 minus 2i would be another complex zero by using the conjugate theorem. So that means x minus 2 plus 2i. So that's the 0. What else could be the 0? X minus the quantity, 2 minus 2i. And now right here for the divisor, we just want to regroup them. So it's x minus 2 quantity minus 2i. And then the other one is similar. So it's x minus 2. And then this one plus 2i. Okay, so this one is set up the extra parentheses. Okay. And then this one, the divisor, will be considered x minus 2 quantity square minus 4i square. So which means that it's considered plus 4. So x squared minus 4x plus 4. So the divisor would be considered x squared minus 4x plus 8. So using the divisor and then divide it from the dividend, and then you get a brand new quotient. So the quotient also from there, you can either factor or can perform that P over Q rational zero theorem with the synthetic division to find out the rational zeros or the complex zeros. Okay, so now let's see what else that we have for this. And for the piecewise functions, so this one can refer back to the transformations chapter, back to chapter 1, what we did there for the piecewise functions. So I'll just do one example. Okay, so 41. So if you started off with that negative 3x to the power of 4, so this one is considered exponential decay because the reflections. And also this one you can set up that the table, easy table. So plug in 0, so you got 3 to the power of 0, nothing, negative 1. So 0 comma negative 1. Well, we do know that this one is restricted with everything that x is less than negative 4. But you can always start it from the original, the parent function first. And then plug in another number. So let's say 1. So 3 to the power of 1, then that would be 3. So negative 3. So 1 comma negative 3. But this one is getting close to anything that's less than negative 4. So plug in anything that's less than negative 4. So it looks like this one is kind of getting close to the x-axis for the asymptote. So most likely this part of the graph is going to be like this. Okay, so for this region here, we can just cut it out. Okay, so because that's restricted with that x is less than -4. Okay, so this part of the graph, just keep it open circle. And then for the other one right there, that's a log functions. So h, VA, which is -4. So at -4, there's a VA. If you notice that the base is not shown, so that means it's considered 10. So in order to make this one log base 10 of 10, so x got to be 6. So x equals 6, log base 10 of 10, then that'd be 1. So if this one turns out to be 1, log base 10 of 1, then that'd be considered 0. Because 10 to the power of 0, then that's 1. So x equals -3 right here, then that'd be all 0. So that means the other part of the graph is going this way, in between -4 all the way to 3. Okay, goes up like that. And keep that in mind, this one, it's not getting close to it, okay? And this one at 3, so it's open circle. Okay, again, this one's being cut off. And now what about that -x plus 1? -x plus 1, so just sketch the graph normally. So up 1 with the y-intercept. And then it's down 1, 1 over to the right. Down 1, 1 over to the right. Keep going. Down 1, 1 over to the right. And for anything greater than 3, down 1, 1 over to the right. So it's all that right here. Okay, so simply connect them. Like this. Okay, piecewise function. Okay, search the arrow. It shows the arrow right here. The left bound, the right bound. And also the VA, you can erase that VA. Okay, so basically just like this. Oops. So we don't need that VA. Okay. So now let's see what else that we have for the rest of this. Excuse me. Okay, what about the limit? Finding the limit, one-sided limit, or the limit at the exact value with that the piecewise functions, or the one with the absolute value. So we'll take a look at that, this one right here. Okay, so if that's a one-sided limit, so this one basically we just need to find out the limit either coming from the left or from the right. So obviously this one is coming from the right, but that the thing is, before we plug in the number, let's simplify this expression. So limit x approaches 5 from the right. So we do know that x minus 5 for the function, absolute value of x minus 5, so that means 5 unit shifted to the right. It's a V shape. So that's coming from the right. So that means it's going to be positive. So it's x minus 5 over x minus 5. Reduce, reduce, positive. So that means this one is going to be what? Positive 1 for the limit. Okay, because that's just one-sided limit, so we only have to verify one side of the limit. But now, what about the limit? We need to find out that at the exact value, like 52, excuse me. So this one, we need to verify the limit from both direction. Okay, so the limit from the left and also the limit from the right. So from the left, and then the limit from the right. So from the left, we do have 5 times negative x plus 4. And then the other one down the bottom, x plus 4. Reduce, reduce. So what's left here? It's negative 5. And then the limit from the right, so it's 5 times x plus 4 over x plus 4. And the limit would be 5. And as you can see, that limit from the left, it's not the same as the limit from the right at negative 4. Therefore, the limit at negative 4 of f of x does not exist, DNE. Okay? So now, and the last part of this, it's all about the trig identity, the proof. Okay, so 53. So you want to show that the complicated side of the equation is the same as the right hand side, this simplest form. So tangent of x, 1 plus cosine of 2x. So for those you might be wondering what we can do with this. Well, this one you can just multiply it out. Okay, so 1 over tangent of x. So 1 cosine of 2x can be written as 1 minus 2 sine square of x. Okay, by using the Pythagorean, well, not the Pythagorean, the double angle identity. Okay, so what we notice, so 1 minus, well, 1 plus 1, then that'll be 2. Okay, so 2 minus 2 sine square of x. Okay, so it's a rational. Okay, so another thing that we can do here, so this one we can take out that 2, so 2 tangent of x, and then it's 1 minus sine square of x in the denominator. By using the Pythagorean identity, so this one is considered 1 over 2 tangent of x times cosine square of x. Okay, now this one got to be very careful. So denominator, it's considered 1 over 2 sine x cosine x. And then this one here, cosine square of x, reduce. Reduce. So what's left here? It's just considered 1 over 2 sine x cosine x. And what is that? Condensing it, so it's the double angle identity of sine. So sine of 2x. And that's what we have on the right hand side. So ditto. Okay. And then the rest of this, they're quite similar. So make sure that you need to refer this one back to chapter 7. So 7.1, 7.2, 7.3. So verifying the trigonometric identities. Okay, so that's it. So thank you for watching the entire video today. So good luck to your final. And I'll see you guys next time. Have a great one.